Welcome back to our course on memory device technology for AI/ML computing. Please try to recall what we were covering the last time, what we had covered in the last session. We were looking at some specific practical examples of how memory hierarchy is actually implemented into high-end consumer electronics products. The two examples we looked at is the Samsung's Galaxy S20 phone and the MacBook Pro. We have some specific companies which do a tear down, which is basically a detailed analysis into how different chips are placed into the motherboard of these products. This also gives some information or insights to its competitors. But for our course, it gave us some insights on how memory hierarchy is actually implemented in the motherboard of these high-end consumer products. Here we saw some very interesting insights in the S20 Galaxy. If you remember, we saw how generally DRAM technology is out of chip memory because the DRAM cells or the DRAM technology consists of one transistor and a highly scaled capacitor. This has to be fabricated in a completely different foundry because the process technology is very different. However, through advances in packaging and co-packaging technology such as heterogeneous integration, Samsung is able to co-package your 12 GB DRAM cell or DRAM chip along with your CPU subsystem. In the MacBook Pro, we got some specific insights into the footprint of DRAM versus NAND flash. The DRAM was only 8 GB. The NAND flash here consuming almost same area was 256 GB. And we saw that is because of the integration density, right? Not just because of the cell, but also the peripherals. With these, we also looked at what is the difference between NAND and NOR flash. NAND flash is sequential, NOR flash is random access, and the importance of EEPROM. This gives us a very good platform to start our next discussion, which is on global semiconductor market trends. So let me ask you a question. How big do you think the semiconductor market globally is in terms of billions of dollars? As you can see in this particular chart, that the current size of semiconductor market in 2025 is roughly in the order of $750 billion. What does it look like in comparison to the GDP of countries? So what is GDP? The full form of GDP is gross domestic product. Gross domestic product is the price of all goods and services produced in a country in 1 year. So the entire semiconductor market per year is roughly equivalent to the GDP of Switzerland. And if you have to put them in the list of countries, only semiconductor manufacturing or the semiconductor market will lie 21st in the GDP list just after Switzerland. The other important aspect to look at is, good, currently it is $750 billion, but what is the rate of growth? To measure the rate of growth of any company or any economy, we generally use a term called CAGR. CAGR or CAGR. It is nothing but the compounded annual growth rate. Compounded annual growth rate. This is not simple interest, it is compound interest. So year on year compounded, how are a company or in this case the semiconductor market growing? And the number that you see over here is roughly 8.8 or roughly 9%. So how do we find out whether this number 9% is a small number or a big number? So we can look at it from two different perspectives. First is to look at a thumb rule when you deal with this number in CAGR. So a thumb rule that I want to suggest to you is, if you want to find out whether a particular organization, or in this case semiconductor market, is growing, if you have the CAGR number, which is roughly 9, all you need to do is divide that number with 72. So 72 divided by 9 is roughly 8. CAGR of 9% roughly means that the rate of doubling, or the semiconductor market will double every 9 years. This is what is indicative of this CAGR rate. And at this growth rate, it is projected that by 2032, your semiconductor market will become equivalent to $1.3 trillion. That is a huge number. And if you look at projections, it is not very wild to guess that semiconductor manufacturing soon from 20 in the GDP list will go to 15 or even 10. When I was teaching this course a few years back, 3 years back, it was 24th in the GDP list. Just in a short time, it has now reached 21 in the GDP list. Why is this happening? Because the rate of semiconductor manufacturing growth is much higher compared to big European countries. So, do you know what is roughly the growth rate in Europe? It is roughly 1%. For US, it is roughly 2.5%. Even India, compared to semiconductor manufacturing, is not doing that great, because India is also growing at roughly 5 to 6%. So the point I wanted to make is that semiconductor manufacturing is alive and well. However, our course specifically deals with the memory segment. So let us look at the memory segment. What is the rough estimate of the size of the memory segment? And as you can see, at 2025, you can see that it is close to $160 to $170 billion, which is roughly equivalent to the GDP of a small European economy such as Hungary. But it is my contention that what is given in this chart may not really be correct, and the actual estimate of what is the memory's share in the entire global semiconductor market might be much larger. So I will explain why that is the case in the next slide, but take a moment to pause and analyze, why do I make this statement that the current $160 to $170 billion number is a gross underestimate. Think very carefully. We will be discussing the answer very soon. Okay. What is the share of semiconductor manufacturing country-wise? Here we see that still the United States captures more than 50% of all of the semiconducting market manufacturing, followed by South Korea and Japan. Why is the United States such a powerhouse when it comes to semiconducting manufacturing? It is got to do with the fact that most of the large foundries in the world, whether it belongs to Intel, Global Foundries, all are in the United States. Here I want to draw your attention to a very tiny country in Asia, in Southeast Asia, which is Taiwan. Taiwan has a very tiny population of only 2.5 crores. It is smaller than the population of the state that we are now here in Telangana. The population of Telangana is 3.5 crores. The Taiwanese population is only 2.5 crores. Compare this to the population of Europe, which is roughly 70 crores. or 700 million. You see, in semiconductor manufacturing, the share of Taiwan and Europe is almost the same. Please recall that some time back, just in 1980s, Taiwan was not a very rich country. However, from 1985 onwards, their government made specific policies and plans to invest heavily into semiconductor manufacturing. Thus was the birth of a very famous company, which a lot of you might be familiar with, the TSMC, or Taiwanese Semiconductor Manufacturing Company. And this has pushed their economy to such levels that they are one of the highest in per capita GDP. So per capita GDP means your total GDP divided by your population. That is highest in amongst all the Asian countries, if you leave out Singapore and some of the oil-rich OECD countries. So this is the target that we want to even achieve through the latest Indian semiconductor mission. The government of India has now invested to the tune of $10 billion to make sure that India can become self-reliant in the area of semiconductor manufacturing. Why is this important? Because the government has realized, not just our government throughout the world have realized that being self-reliant in semiconductor materials and devices manufacturing is important, as important to their strategic growth as is national security. So they have been kept in par. Because if you really want to destroy the economy of a country, you can just disrupt the semiconductor supply chain. That is why all countries around the world, including the US through its CHIPS Act and our own country through the Indian Semiconductor Mission, is investing heavily in trying to make their own countries self-reliant on semiconductor manufacturing. So this is how important semiconductor manufacturing and in some part our course is to the overall growth of our country. Having said that, I want to go back to the question which I asked in the previous slide. I said that the previous graphic that we saw suggesting that the size of memory market is only $170 to $180 billion is a gross underestimate. And I asked you, why is that the case? To give you a further hint why that might be the case, let me indicate to you that the entire memory market in principle can be divided into two parts. And the first subdivision is the standalone or the off-chip memory market, where you get separate dies or separate packages, right? So as you know, memory can be both on-chip or off-chip. What were the essential elements of off-chip memory? Everything except the caches. So as you can see over here, the DIMMs or dual inline memory modules, in which these DRAMs are integrated. We will study more about DIMMs when we look at DRAM along with the NAND flash. So NAND flash is also a very important standalone off-chip memory. We saw that although the segment is very small, NOR flash is also another important off-chip memory. This is now being supplemented with new storage class memories such as 3D Xpoint from companies like Intel and Micron, and also new magnetic random access memories, resistive random access memories, which form the storage class memories. All these are a part of standalone or off-chip memory market. This segment itself, back in 2020 was estimated to be $150 or $140 billion. And this is the segment wise breakup of the standalone or off-chip memory market. This graph has been taken by a company called Yole. So Yole reports every year releases these reports which tells us how the semiconductor manufacturing across different segments is performing and growing. In this schematic, you see there is a very interesting observation that we can make. We discussed that when you see DRAM, when you buy a DRAM chip, it is roughly 4 to 64 GB, whereas the NAND flash starts from half a TB. However, if you see in absolute dollar terms, the size of the DRAM market is more than 50% of the off-chip market. NAND flash is much smaller, to the order of roughly 44%. Why is this happening? So let me repeat the question. Although the size of DRAMs in terms of memory capacity is much smaller than compared to NAND flash, in absolute dollar terms, the size of DRAM market is much larger. Why is this happening? Please take a moment to pause and think. Now, if you have been following this course carefully, you might remember when we were discussing the comparison between DRAM and NAND or DRAM and flash memory, we saw that the bit density in NAND flash is much higher compared to DRAM. Therefore, the cost per bit for NAND flash was also almost 8 times lower. Remember what was cost per bit? Number of dollars you need to spend to buy 1 GB of memory or to manufacture 1 GB of memory. This metric was almost 8 times lower for NAND flash as compared to DRAM. And this explains why DRAM is a much more expensive technology compared to NAND flash, and therefore in absolute dollar terms they occupy more space in this pie chart compared to NAND flash. What are the other small elements in the pie? One is NOR flash. We saw in our MacBook Pro breakdown that NOR flash, the amount of NOR flash was, or the capacity of NOR flash was in few MBs, 8 MB, but they also are quite expensive. So they take up roughly 2% of the standalone market, followed by your new class of memories, eNVMs, such as magnetic RRAMs, etc. However, this is just one subdivision of the total memory market. Can you take a moment to pause and guess what could be the other major component of the memory market? That would be your on-chip or embedded memories. Your on-chip or embedded memories. The first is your off-chip memory, second is your on-chip memory. And now you will be very surprised to see that the size of on-chip memory is roughly equivalent to the size of the off-chip memory. It is close to $130 billion. Again, why is this the case? Please recall the size of on-chip memories, which constitutes primarily of SRAM, is very, very small. SRAMs L1 and L2 is in the order of KBs, whereas L3 is in the order of MBs. However, DRAMs and NAND flashes are in the orders of GBs and TBs. Nonetheless, the cost of manufacturing SRAMs is much larger. Why is this the case? Let us look and try to understand. And this particular graphic, which is in front of you, is a good indicator of why that is the case. So here we have illustrated a quad-core processor from Intel. You can see Core 0, Core 1, Core 2 and Core 3. What is very remarkable in the graphic is if you compare the size of the L3 cache is really comparable to the size of all the 4 cores. Let us also remember that each of the core also has embedded L1 and L2 caches. In addition, please let's look at the size of the memory controller. So it seems through this graphic that roughly 60 to 70% of the footprint in a logic chip is dedicated purely to caches and to memories. And that is why the relative cost of caches and memories could be estimated to be 60 to 70% of the size of your logic market. So if we go back to the previous slide, you see we had a separate segment for the logic devices, but it is important to note that 60 to 70% of this particular segment could again belong to the embedded SRAMs. And therefore, we had made the claim that the size of the memory market indicated in this graphic of $160 to $170 billion might be a gross underestimate. Okay, now that we have understood this, we see that since more than 50% is dedicated to memories, it is logical to think that this part of the segment will be captured by the companies who make advances in logic transistor devices and allied manufacturing facilities. These are Intel, TSMC, Global Foundries, and a few other companies. Okay, so in essence, what we saw was memory market cannot be restricted only to its off-chip or standalone components. There is a big component of memory footprint within the logic subsystem also. With this, let us try to evaluate or understand where different companies are trying to innovate such that they can get larger and larger share of the semiconductor memory market pie. So what are companies essentially trying to do? So basic strategy that companies are trying to employ is they are trying to reduce the cost per bit while maintaining speed. This term that I have mentioned over here, while maintaining speed, becomes very, very important. Why is this the case? Let us try to understand why this caveat is very important. A simple way to understand that would be the best way to reduce cost per bit would be essentially to reduce the memory footprint. However, just reducing the memory footprint is not enough. The interconnect or the wires which are used to access the memory, the size of these interconnects also need to be reduced. As you may understand, an interconnect wire, when you start reducing the size, the resistance of this interconnect will increase, and therefore the latency will increase, and you may or may not be able to maintain very high speeds when you increase bit density. So just as we have been appreciating throughout the course, there are no free lunches. Once you start optimizing on one end, another parameter, you have to make sure that it doesn't go out of bounds, right? So let us understand the story of what drives market trends. The answer is through innovation, through our first example of SRAM. Since SRAM consists primarily of the 6T cell, it is natural to understand or natural to guesstimate or estimate that innovation in 6T SRAM cells are primarily driven by innovations in transistor scaling. Why is this the case? The smaller and more compact you can make the transistor, smaller will be the size of your individual SRAM cell. For those who have done a course in transistor technology or even semiconductor devices, you may be familiar with the Moore's law. The Moore's law was an empirical guess made by Gordon Moore from Intel that the number of devices you can pack into the same footprint will double every 18 months. And quite remarkably, the Moore's law of scaling. And how was that possible? That was only possible by reducing the size or the footprint of the fundamental unit of computation, which is the transistor. Right? So this law of transistor scaling has also benefited SRAM cells because you are able to now pack in more bits into a small footprint. This, along with the ability to do extreme lithography, has made sure that SRAMs continue to give better and better performance as time passes. Quite remarkably, when a new transistor technology node is invented by Intel or developed by one of the manufacturing companies like Intel or TSMC, the SRAM performance is one of the technology qualifiers. What is the meaning of technology qualifier? It means it's an indication or a parameter of how good the current proposed technology is over its previous generations. So SRAM latency, and what we will see when we dig deep into SRAM, we will talk about Shmoo plots are a very important technology qualifier. So let us see how reducing the size of the transistor has enabled the scaling of the SRAM cell area. To understand this, we need to be familiar with what is that parameter which is being scaled in the transistor technology. It is called the contacted gate pitch. So what is the contacted gate pitch? The contacted gate pitch is the gap between the gate finger, the starting of the gate finger of one transistor and the next neighboring transistor, as you can see from this particular diagram. The contacted gate pitch consists of three main elements. The first is the WC, or the width of the contact of the source and drain metal contacts, plus the gate length LG, and 2 into the W spacer. So the W spacer is the space between the contact and the gate finger, right? So the contacted gate pitch is reducing every technology node, as you can see, by a factor of 0.7x every 2 years. Why is this number 0.7x very special? Because it is roughly 1 by root 2. 0.707 is 1 by root 2. So if the linear dimensions in the chip is reducing by 1 by root 2, you can expect that the area reduces by 1 by root 2 the whole squared, which is half. And therefore, SRAM cell area is becoming half every 2 years. And the other way of saying this would be that the number of SRAM cells you can embed into the same footprint is doubling every 2 years. So what we wanted to essentially illustrate is through advances in transistor technology, SRAM technology is also improving. Here, I would want to illustrate this with another example. On the top, we see that what was the footprint of the SRAM cell in the 32 nanometer node. It was roughly 0.71 micrometer square. So to implement one SRAM cell of 6 transistors, you can see the 6 transistors over here. You have to pull-up transistors, 2 pull-down transistors, and 2 access or pass gate transistors, you required roughly 0.71 micrometer square. But when we went to the next technology node, which is the 22 nanometer technology, we were able to implement the same design in a high density cell configuration, and for the first time SRAM cells became smaller than 0.1 micrometer square. Now, what facilitated this change from 32 nanometer technology node to 22 nanometer technology node? So what changed? As you may know, the planar transistor became a FinFET design, and this is something we will discuss further when we talk about SRAM cells. Next innovation that we would like to look at, which is driving market trends, is in the DRAM technology, which comes next in the memory hierarchy. So the DRAM cell, which is one transistor, one capacitor DRAM cell, the primary factor which was deciding how well you can scale DRAM technology a few generations earlier was the ability to pattern things or lithography. However, in current technology nodes, what is driving the scaling of the DRAM cell is the footprint that the one capacitor in the capacitor in the DRAM cell is occupying. This, along with trying to make interconnect parasitics manageable. Just as we discussed a few slides back, when you try to scale technology nodes and try to reduce the size of the interconnects which from which you access data from the memory cells, the parasitics start becoming a problem. So how do you manage both these factors? Capacitor footprint and interconnect parasitics determines how well you can scale the DRAM cell. Like the CGP or contacted gate pitch was the technology indicator in an SRAM cell, for a DRAM cell it happens to be the metal half pitch. So what is the DRAM metal half pitch mean? It is nothing but the gap between two neighboring cells or the gap between two neighboring bit lines. Within few classes, we will see what a bit line is, but just a heads up, the bit line is nothing but that which connects two memory cells. So here we want to see how the half pitch of DRAM cell is being scaled. As you can see, the DRAM technology roadmap is driven by four main companies. It's Samsung, SK Hynix, both are South Korean companies, Micron, which is an American company, and Nanya, which happens to be a Chinese company. If you see how these DRAM cells were scaled, initially you will see NTC or Nanya's technology was going from 30 nanometers, but currently if you look at the technology indicators, you see a lot of numbers like 1Y, 1Z, 1 alpha, 1 beta. What are these values of X, Y, alpha, beta? So the essence is that since DRAM technology is so competitive, you do not want your competitors to know what is your next technology node. But on the other hand, you also want to convey that you are going to next technology node. And therefore people, just like in mathematics or algebra, we use X, Y, Z as variables, which we initially don't want to reveal. Similar thing is done by these technology companies. As we know, these numbers are nothing but your metal half pitch or your distance between two bit lines. And I have heard from some of my friends in some company which I cannot reveal here, that the Y technology node is already in 15 to 16 nanometers. That means one Y technology, the gap between two DRAM cells is only 15 to 16 nanometers. So as we can see, there is a rapid change in not just the SRAM technology, but also the DRAM technology. And there is intense competition between companies to do better than others and capture more of the market space. With this, let's conclude today's discussion. And in the next class or the next session, we will look at what are the innovation trends in NAND flash technology, and we will also see these focus towards innovation, how it is enabling different companies to capture more of the market space. Thank you.